Assalamualaikum and good day to all of you. In this video, I will explain about tutorial chapter 3, which is magnetostatic. So we proceed to number 1, question 1. You can refer to slide 29 on how to solve this the question 1 answer. So the question give you, okay, in a cylindrical coordinate system, a 2-meter long straight wire carrying a current of 5 ampere in the positive z direction is located at r equal to 4 cm, phi equal to pi over 2, and z is between -1 to 1 meter. Given B, magnetostatic density 0.2 cos phi AR Tesla. What is the magnetic force, which is Fm, acting on the wire? Okay, if you refer to slide 29, this is the equation. Fm equal to I times L cross B, vector B. Okay, so length of the wire is given, okay, which is 2 AZ, 2 meter long, and AZ is positive Z direction. So that's why for L is 2 AZ. Current is 5 ampere and magnetic and B is 0.2 cos phi AR. This B is already given in the question, so you just need to substitute, okay, and then solve L cross B. Okay, the first row is for L, so we know that first the L here is 2 AZ, so you just need to put 2 here under AZ column, and for AR and AP is just simply put 0. And for B, vector B, you already know that it is only at AR direction. So 0.2 cos phi put under AR column, and another 2 AP and AZ, just simply put it 0. So solve Fm equation. We will get this one, 2 cos phi AP. And don't forget, at phi equal to pi over 2, this is given, and F equal to negative AX. Okay, hence Fm equal to negative 2 cos pi over 2 AX equal to 0. So when we solve this magnetic force, okay, you will get 0. So what is the meaning of this question? Meaning that Fm equal to 0, meaning that carrying current in closed circuit under uniform magnetic field B. You can refer this info by referring to slide number 30. Okay, that's all. We proceed to question number 2. Now we proceed to question number 2. The question gives you 2 infinitely long parallel wires carry 6 ampere current in opposite directions. Calculate the magnetic flux density at point P in figure below. So we have 2 conductors. The first conductors carry 6 ampere current in upward position, while the second conductor carry 6 ampere current in opposite direction. Okay, so the distance between these 2 conductors is 2 meter, and point P is located here, and you need to find magnetic flux density at point P. Okay, the solution. So you need to refer to slide number 8 to find the magnetic flux density, which is B. So we know that if you refer to slide 8, the equation is based on the infinite long wire. So the equation is B equal to mu naught I current divided by 2 pi r AV. So we know that in order to find magnetic flux density at point P, you need to find B1, which is magnetic flux density B from conductor 1 to P, and from conductor B, conductor 2 to point P. So for B1, you just need to substitute all the values for B1 and B2 based on the equation given. So the value of mu naught is 4 pi times 10 to the power of negative 7 times 6. 6 is the value of the current, and divided by 2 pi times 0.5. 0.5 is the location from conductor 1 to P. Okay, this is the conductor 1 from P. The location, the distance between these 2 points is 0.5 meters. So you just need to substitute value of 0.5. And then for AV, okay, don't forget AV because of the equation given is AV plus mu naught permeability times 6. 6 is the value of current for conductor 2 over 2 pi, and then times the distance between conductor 2 to point P. So conductor 2 to point P is 1.5 meter. Okay, don't forget to put the direction of AV. So when you add up both of the equation, you will get 3.2 times 10 to the power of negative 6 AV Tesla. Okay, now we proceed to question number 3. Okay, this is the question. The question gives you a radial magnetic field H equal to 1.5 times 10 to the power of 6 over R cos P AR ampere per meter exists in free space. Find the magnetic flux crossing the surface defined by a phi between 0 to pi over 3 and z between 0 to 3 meter. Okay, if you try to draw, okay, you will get the space is something like this one. Okay, 0 to pi over 3. Pi over 3 is 180 over 3. So it is about 60 degree. So here is 60 degree. Okay, and then the surface is between 0 to 3. So the surface is facing to AR direction. Now the question asks you to find the magnetic flux. Okay, so you need to refer to slide number 22. Flux is equal to B vector of B dot ds. So we know that B is equal to mu naught H because the question gives you H, magnetic field intensity H. So you just need to replace mu naught h into this equation, you will get like this. And if you see here, the surface, differential surface, is facing towards AR. So it is DSR. So DSR, if you refer to the table in chapter 1, you will get R dV dz AR. So just replace R dV dz AR into this equation, you will get like this. R dV dz AR. And replace also the magnetic field intensity, which is 1.5 times 10 to the power of 6 over R cos phi. Okay, so you know that AR dot AR is equal to 1. So we can remove AR here, and phi is between 0 to pi over 3, and Z is between 0 to 3. And then solve it. So you will get 1.5 times 10 to the power of 6 mu naught sine phi, okay, 0 to pi over 3, and Z 0 to 3. And then solve the integration. You will get like this. And just use your calculator, and the answer is 4.897 Weber for this answer. So 4.897 Weber is the magnetic flux crossing the surface here. Okay, now we proceed to question number 4. The question gives you the rectangular loop shown in figure below is coplanar with infinitely long straight wire carrying the current I equal to 20 ampere. Determine the magnetic flux through the loop. Okay, this is the loop. This is the loop. Coplanar with infinitely long wire straight carrying current. This long wire carrying current I equal to 20 ampere. So you need to find the magnetic flux that through the magnetic flux through the loop. Okay, so first, okay, this is the equation, the rest equation for infinitely long wire. So given the equation, okay, you need to use this equation since the question gives you infinitely long straight wire carrying current I equal to 20 ampere. So this is the best equation that you can use, okay, to find the magnetic flux. Okay, so just substitute mu naught is equal to 4 pi times 10 to the power of negative 7, and then current given in the question is 20 ampere. Okay, 20 ampere, 4 pi times 10 to the power of negative 7 times 20 over 2 pi r. Okay, 2 pi r AP. So when you simplify this equation, you will get this one. Okay, 4 times 10 to the power of negative 6 over r times AP. Okay, now we need to find the magnetic flux through the loop. We know that, okay, from the lecture note slides, given the equation to find magnetic flux is P equal to B dot ds phi. Okay, why ds phi? Because the loop here is facing towards phi direction. Okay. Okay, so ds phi is dr dz AP. So just substitute all the values. you already have B from the previous solution. Okay, so just substitute the value of B, and then substitute DSP here into this equation. So AP dot AP, you will get 1, so we can just remove AP, and then so it is considered that this one actually is the radius. Okay, this is actually something like this one. Okay, so this is one part of the cylindrical. So we can assume that, actually it is the cylinder. Okay, so we only take one surface of the cylinder. So that's why this surface is facing towards P direction. Okay, now we can consider this one is R. Okay, R between 5 cm to 20 cm. So that's why dr here, okay, we put from centimeter is 0.05 meter to 0.2 meter. Okay, dz is the height of the coplanar, the loop here. So the height is between 5 cm to 30 cm. So that's why I put here 0.05 to 0.35. Okay, meter. So when we solve it, you will get this one. Solve the integration part. You will get like this. And then after you solve it using your calculator, you will get 1.66 times 10 to the power of negative 6 Weber. Okay, now we proceed to question number 5. Actually, question number 5 is the one of the question in final exam for previous semester. So, okay, we proceed to the question first. Okay, the question is a vector magnetic potential of a current distribution in free space is given by A equal to 20 exponent negative 2R sin phi A Z Weber per meter. So given the potential, magnetic potential, okay, this is A is magnetic potential, and then you need to calculate the magnetic flux crossing the surface defined by R equal to 2 phi between 0 to pi over 2 and Z between 0 to 8. All distance are given in meters. So first, okay, you can draw, okay, the surface. The surface is between this is 180 over 2 is 90 degree. Okay, 90 degree. And then Z is from 0 to 8. Okay, radius 2. Okay, so you can draw the surface. Surface. Okay. Facing towards the AR direction. Okay. So the question asks you to calculate the magnetic flux crossing the surface. Okay, first you can refer to slide number 22 and 23. Okay, this is the equation that I got from slide 22. Okay, you can choose whether you want to use this or towards differential surface or towards differential length to find the magnetic flux. So in this question, I prefer using surface integral. So I will use this surface integral. Okay. Maybe later on you can find using differential length to compare the answer. So we know that DSR is because of the this surface facing towards AR. So that's why you need to refer to DSR. So A cross del cross A. So this equation given is based on the table in chapter 1. So I just write it back. And okay, if you see the question here, okay, this is the given magnetic potential. Actually, it is only referred to AZ. Okay, because of the Z direction, this is AZ. A is potential, Z is referred to direction. So, if you see this equation, you can eliminate, you can remove the symbols that is not related. So we only have AZ, we don't have AP, so we can remove it here. You can remove this one and this one also. Okay, and only left 1 over R, this one, DAZ over dPAR, okay, this one, and then plus negative, okay, negative DAZ over dRAP. So substitute the value of AZ here, AZ, okay, so and solve the differentiation. You will get this one after you solve the differentiation. And then okay, so after you already have the value of the equation of del cross A, you can substitute into this equation again. Okay, this one, del cross A. Okay, so that's why after that, after you substitute, you can find the magnetic flux. The magnetic flux here. Okay, substitute the answer. This is from del cross A R dphi dz AR. Okay. R dphi dz AR is referred to DSR. Okay, DSR. And then phi is between 0 to 90 degree. Given in the question, Z equal to 0 to 8. Okay, so solve it. Remember, this is AR times AR equal to 1 by AP times AR equal to 0. So you can just remove these terms. Okay, the second terms here. So after you solve it, you rearrange it back. You will get this one. Okay, and then solve the integration part. Okay, so you can after you solve the integration part, you can substitute the value of R equal to 2, since the question give you radius of the surface is when R equal to 2. So R equal to 2 is the fixed value. Okay, so you can substitute R equal to 2 here. You will get this one. and then use your calculator, you will get the answer of magnetic flux is 2.93 Weber. Okay, that's all for question number 5. Okay, now we proceed to question 6. Okay, the question give you, consider an infinite filamentary wire making a 90-degree bend at the origin, as illustrated in figure below. The wire is a part of a very large circuit carrying a current of 0.8 ampere. The diameter of the wire is 4 mm. Okay, so this is the figure. Okay, so this is infinite. Okay, the wire is come from here, negative infinity to negative infinite. Okay, to the positive infinite. And the current is carrying from negative to positive. And bend, it is bent at 90 degree at the origin. Okay, so the current carrying by the conductor is 0.8. The diameter of the wire is 4 mm. And then the question asks you to determine the magnetic field intensity H induced by the wire at point P 200. Okay, point P is here. P is 200. So you need to find the magnetic field intensity, okay, induced by the wire at point P. Okay, by employing Biot-Savart law. Okay, so firstly, okay, you can refer slide number 9. This is the equation based on slide number 9 and based on the line. Okay, magnetic field intensity for the line. So H equal to I over 4 pi integration dl cross r over r cube. R cube is the magnitude. Okay, this is the magnitude and this one is the vector of r. So firstly, okay, we have the equation of H, but firstly you need to know what is H1 and H2. Okay, actually H1, if you refer to the figure here, okay, H1 is from the conductor, the first conductor here. Actually, this is only one conductor and it is bent at 90 degree. So we need to find the magnetic field intensity from this part to this point, and then from this part to this point. Okay, it is something like this. Okay, so this is H1. You need to find H1, okay, and you need to find H2, and then add up both magnetic field intensity. So, okay, first you need to find A, okay, which is H1. Okay, so H1 is equal to I over 4 pi integration dl1 cross r1 over r1 cube. Okay, so r1, vector r1, this is we need to find r1, magnitude of r1, and also this, all of this. Okay, so r1 is actually, this is general equation, x2 minus 1 ax plus y2 minus y1 ay plus z2 minus z1 az. So x2 okay, minus x1 is, okay, this is x, okay, x2 is from 2, okay, because of this point 2, minus, okay, this part of the wire is located at x equal to 0. That's why 2 minus 0. Okay, this is 2 minus 0, ax, plus 0 minus y. Why 0 minus y? Because, okay, at this point, y is 0. Minus y. Y is, okay, along the wire. Okay, we don't know the point of y, whether it is at y equal to 1, 2, 3, or etc. So it is the best to use 0 from this P point here, minus y. Put general y here. 0 minus y. So solve it, you will get 0.02 ax minus y ay. Okay, now you have the value of, okay, the solution of R1. And then from R1, vector R1, you can find the magnitude. Okay. Okay, how to find the magnitude? Okay, you already have the vector here. And then use the vector to find the magnitude. Okay, so magnitude 0.02 squared plus y squared. Okay, set. Okay. So now you need to find DL1. What is DL1? You already have R1, R1 cube, and DL1. You need to find DL1. What is DL1? Actually, DL1 is equal to DLY, length of the wire at y-axis. So it is equal to DLY. DL1 equal to DLY equal to negative DY-AY. So negative DY-AY is coming from the equation in the table chapter 1. Okay. Okay, now you need to solve it for DL1 cross R1 because of the equation. DL1 cross R1. So, okay, this is for DL1. This is for R1, vector R1. So DL1 is negative DY AY, okay, because of the first row here, DL1. Okay, for R1, vector R1 is, we know that in this 0.02 ax minus y ay. So 0.02 ax minus y ay. Okay, so solve it, you will get negative 0.02 dy az. Okay, so you already have all the values, DL1 cross R1, and then you have the magnitude. Okay, so now just substitute all the values in the equation, you will get like this. Okay, so dy, so the integration is towards dy, so dy is from negative infinity to 0. So solve it. Solve the integration part from negative infinity to 0, and then after you solve it, substitute. Okay, you will get like this, 0 minus negative infinity over infinity, you will get negative 1 lah. Okay, 1. Okay, negative with negative is positive, so this positive 1, and then you just need to solve this part, you will get negative 3.183 az and paper method. Okay, now we proceed to H2. Okay, now we proceed on how to find H2. H2. So the procedure is similar to H1, but you just need to okay, I proceed with the equation first. So H2, in order to find H2, which is here H2, you need to consider previously H1, you need to consider this part of the wire, but for H2 you need to consider for this wire. Okay, so current over 4 pi, integration of dl2 cross r2, vector of r2 over magnitude of r2 cube. Okay, now we need to find the r2, vector r2. Okay, x2 minus x1 ax, y2 minus y1 ay, plus z2 minus z1 az. So this is the basic equation, general equation that you need to follow. So for x2 is from 2 cm to 0, minus 0. ax, why? Because 2 cm is come from 2 at point P, minus 0. 0 is meaning that this part of cables is when x equal to 0. So plus 0 minus z, az, because okay, P is at 0 and then z is along the wire. Okay, so 0 minus z. Okay, and y, this part of cable is when y equal to 0. Okay, so simplify the vector r2, you will get this one, 0.02 ax minus z az. Okay, now you need to find the magnitude. So the magnitude is r2, 0.02 squared plus z squared, z. Okay, so we already have the magnitude and also the vector. So now we need to find dl2. So dl2 actually is equal to dlz, since the cable is follow z direction. Okay, that's why it is dlz. So if we refer to table in chapter 1, dlz is equal to dz az. So because we want to satisfy the formula, which is dl2 cross r2, so solve dl2 cross r2, you will get the answer is 0.02 dz ay. So this row is for dl2 and this row is for vector r2. Okay, so dl2, you know that dl2 dz az, so dz az, while r2 is, okay, refer to this one, 0.02 ax. Okay, okay, so this is 0.02 ax, no ay, okay, no ay, so minus z az, so put minus z az. So after you solve it, you will get 0.02 dz ay. Okay, now H2. Okay, so you have all the values, okay, the equation, and you just need to substitute to the original equation of H2. And then you will get like this, and don't forget to substitute I equal to 0.8 ampere that given in the question. Okay, and then solve the integration part. You will get like this, from 0 to infinity, and then you will get like this, And the answer is 3.183 AY. Okay. Okay, so don't forget the question is wants you to determine the magnetic field intensity induced by the wire at point P. Okay, so you need to add up H1 and H2 and you get this answer 3.183 AY minus AZ ampere per meter. Okay, now we proceed to question 6B. Okay, this question asks you to calculate the corresponding current density J across the wire. So, you need to refer slide 13 on how to find the current density. So, I equal to integration of J dot ds. Okay, so you already know that J, vector of J is equal to actually Jz Az, and df, differential surface, is towards Z direction. Okay, so dsz is equal to r dr dphi az. Substitute the equation of dsz into this general equation, and then substitute also the value of r from 0 to 0.002 to 0. And for phi is from 0 to 2 pi. Okay, this is all given in the question. Actually, the value of radius. Actually, in the question give the value of diameter, and we just need to divide by 2 to find the radius. Okay, so when you solve it, you will get current density Jz in the direction of Z 0.8 divided by 0.002 squared over 2 times 2 pi. Okay, so Jz is 127.32 ampere per meter squared. But in order to find J vector, okay, you need to give the direction. Okay, 127.32 Az ampere per meter squared. Okay, this is the answer for current density across the wire. Thank you.